Hello, everyone. This is a tutorial video to help you with the first part of stoichiometry. Basically, we'll cover the first steps or the general aspects that you should know at the stage for stoichiometry introduction. All right, so let me just share screen. I'll guide you through the same presentation we saw in class, but important to mention that I will go straight into straight into the procedures, and we'll talk about a little bit of the background information that you should know at this point. But in any case, you still have available the presentation if you want to go back and see something with more detail, right? So first of all, like in general terms, what is stoichiometry? Basically is the study or the measurement of different quantities and their conversions, their behaviors in different forms or in different units, right? But back when we saw unit conversion, we were talking about how to exchange from kilograms to grams, from milliliters to liters, like density and all of these different units that were basically the same thing, but with another unit or with another phase, right? Here, we're gonna do pretty much the same thing. It's just gonna be related to chemical equations, chemical reactions, and the different units that we might actually use at this point. So the first thing is to learn or to be sure how to calculate a molar mass. And the molar mass we will use for this the periodic table and our previous knowledge of what we learned back then when we were studying the periodic table of what we call the atomic mass unit, right? So in the periodic table, you can actually see let's say for oxygen, right? You will have element number 8. You will find oxygen, the symbol. You will find the name of this oxygen. And down there below that, you will have this number with the decimals, right? This guy over here, this is the atomic mass unit for oxygen, right? So back then in the periodic table, we were talking about this. At this point, we'll be calling this the molar mass, or basically the mass that actually we're going to be using as reference for this particular element, right? So the molar mass of an element is the same as the one that you have in the periodic table. But what happens if you have, for example, a compound? This compound being water. Well, it's actually, remember when we were talking classification of matter? So we were talking about pure substances. We would have not chemically divisible would be an element, but more than one element together, we would have a compound, right? In this case, compounds are made up of different elements, more than one or more than two elements. So meaning that in order to get the molar mass of a compound, we first need to know the molar mass of the element. So for this example, we can check the periodic table for hydrogen. And what's the molar mass of hydrogen? So it would be 1 point something, right? And for oxygen, we will see that it's actually 15.999, right? In this case, we're going to be using like whole numbers, like with no decimals. So we're going to be rounding up or down, depending the case, the molar mass for each element. So for hydrogen, it would be 1.0 something. So this actually would stay in 1. For oxygen, well, it's actually closer to the 16. So we're going to be using 16 as our reference number, right? So in here, let's see, we have how many atoms of hydrogen in this compound? Well, there's a subscript for hydrogen. That means there's 2 hydrogens, right? This is the amount, not the charge. This is the amount. So that means we have, let's put here, number of atoms. For hydrogen, we would have 2 atoms, right? And the molar mass of hydrogen, according to the periodic table, already rounded, it would be 1, right? For oxygen, we would have, in this case, there's no subscript. That means there's only 1, right? So we're gonna have number of atoms, 1, and the molar mass for this guy is actually 16. Remember, we rounded up. So next, we actually need to get the total molar mass per element in this molecule, right? So the total molar mass in this compound for hydrogen would be 2 atoms times the molar mass of each, which means is 2, right? What about for oxygen? Well, we only have 1, and this one measures 16 or weighs 16. So now that we have the total per element, we're just gonna add them up. So 16 plus 2, we have 18. Now these 18, the unit will be 18 grams per mole, right? That means, pay attention to this. If we remember from the chemical formulas or the chemical equations, we would say that this guy, if we put a 1 here, this is 1 mole of water, right? Which means this unit, this is mole, the same as this guy, right? So per mole, for each individual mole, this water molecule will weigh 18 grams, right? Or 18 atomic mass units. For now on, we will be using this measurement, which is grams per mole. So think about this for a second. What does this actually mean? Oops. So if we have 18 grams per mole, per each mole, what happens if we actually have here a 2, right? So if we have 2 moles of this guy, well, the total would be 18 times 2, right? So it would be 36 and so on and so forth. So let's go forward with this. Now, these are the instructions for calculating the molar mass. This you have in your presentation. You may take a screenshot as you wish. Now let's see some examples, basically starting from the compound, right? From the chemical formula of the compound. Now in here, take a moment to think about what's the name of this. It's important that you don't forget nomenclature because we'll be keeping using all of this stuff. Balancing equations, nomenclature, all of this is important. So the name of this guy, how would it be? Well, we first need to check the first one, which is sodium. Oops, sodium. And this guy together, right? It has its own proper name. OH molecule, it's called hydroxide. So this guy would be called sodium hydroxide. At this point, it's important that you think constantly about this because if the problem is actually asking you for something starting from the name, you need to still be able to actually translate this guy into a chemical formula, right? All right, let's think about this for a second. So what are we being asked? Sodium, oxygen, and hydrogen. So we need to first search and identify where is sodium, where is oxygen, and what's the other guy? Hydrogen, right? Check out these numbers. So sodium has 22.999. So this guy will round up to 23. Hydrogen has 1.0079. So this one is going to round down to 1. And oxygen has 15.999. So this guy will stay at 16. Well, we'll go to 16, right? All right, so let's pick up these numbers and let's go to our problem. In here, it says calculate the molar mass of sodium hydroxide. So first step, write down the elements for these guys. So sodium, oxygen, and hydrogen. Got it. Step 2, write down the number of atoms for each element. So again, if there's no subscript in here, there is no number for any of them, that means there's 1 for each. So we're going to write 1s for everybody. Number 3, write down the molar mass for each of these elements. Remember, these guys are in the periodic table. So the numbers that we just saw, we're going to bring them back here. Notice there's no decimals, right? It's not like 0.012. No, we're just going to be using whole numbers. Next, we multiply and add the whole thing, right? At the end, this number that we have right here, notice the unit is grams per mole. That means this entire molecule, sodium hydroxide, equals a molar mass of 40 grams per mole, right? Good. So now let's check out another example. Think for a minute what the name is of this compound. How do we call this? So in here, notice we have here a polyatomic ion. And this guy over here, this is a metal. So metal plus metal plus polyatomic ion, this is a salt, specifically tertiary salt, right? So the name for the salt is pretty straightforward, right? So we'll call this potassium, just as the periodic table tells us. And this guy over here, PO4, is called phosphate. So no dramas here, no Roman numbers, just plain and simple potassium phosphate, right? Now, where are these guys in the periodic table? Well, potassium is over here. And then this guy, right? This is different from this one, right? Potassium is a K. P, remember, is phosphorus. It's not potassium with a P, right? And O is oxygen. So we'll pick up these numbers and use them in our next example. So calculate the molar mass of potassium phosphate, right? First, write down the elements for each, right? We're using potassium, we're using phosphorus, and we're using oxygen, right? Now write down the number of atoms for each of these elements that we have in the formula. Notice here we do have some subscripts. So these subscripts are going to be the amounts, remember. This is how many, you can count them, right? So for potassium, there's 3, because 3 is over there. Phosphorus, there's only 1, because there's no subscript whatsoever. And for oxygen, there's 4, because there's the 4, right? Now, we will write down the molar mass for each individual, according to what we have in the periodic table. So if you do pick up, we would have 39, rounded up or down, rounded up for potassium. Phosphorus would be 31, now that we rounded, and oxygen with the same 16. What next? Well, we need to know the total. So we multiply the whole thing and we get the total per element. Now we just plain and simple add these numbers. So we get the total amount for the entire molecule, right? That means that this entire thing, potassium phosphate, will be equal to 212 grams per mole, right? All right, so in here we have some practice exercise. I'll do them right here in the video. You can skip ahead if you don't need any reminder of this. So for the first one, we have calcium and chloride. So first step, we will take calcium. By the way, the name for this is calcium chloride, right? With an IDE. Don't forget about the IDE whenever we're talking about the nomenclatures aspect. Calcium and chlorine, right? Now, how many atoms? 1 for calcium, 2 for chlorine, right? So what about the molar masses of this? So the molar mass for calcium is actually 40, I think. Yeah, 40 point. So if we check the periodic table, it's going to be 40.078. 078. That means that we're going to round this to the 40, right? So we're going to stay with 40. So we're just going to write 40 here. And the molar mass for chlorine is 35.45. That means the 4 goes down, right? So we're going to stay with 35. Now, next step, we actually multiply these guys, right? So we got enough. So we get in here 40 and in here 70, right? 35 times 2, 70. Now we add these guys and we will get 110, right? This is 110 grams per mole for this entire molecule, right? This is the molar mass of the molecule. All right, now for the next one, we have potassium, nitrogen, and 3 guys of oxygen. So we'll put this potassium, nitrogen, and oxygen. How many of each? 1, 1, and 3. The molar mass of each for potassium is 39.098. So that means we'll stay with the 39. Nitrogen is 14.007. So we'll use 14. And for oxygen, we have 16. So how many of each? So we'll have the 39, the 14, and 16 times 3. So you can get your calculator and actually do this faster, right? At this point, it's important that I mention that you can use your own calculator, and it's better that if you get familiar with this, right? Because at the end, each calculator is different. So it is very convenient if you get to know your calculator, and this calculator is the one that you will be using for the exams, right? All right, so this 48 we got for oxygen, we add the 14 and the 39, and we got 101, right? So this is 100 grams per mole, right? This is your molar mass for potassium nitrate, right? What about the next one? We have iron oxide, right? Now this would be, so we put the numbers here, well, then the symbols, then 2 for each, 2 for iron, 3 for oxygens. Iron would be 40, no, 55, 56 actually, 50, it's 55.84. So we'll put 56. And oxygen, 16. So for each one, we get 56 times 2, right? So this is 112, and 36, 16 times 3 would be 48, right? So now we add these guys and we get 112, right? So we get 160, right? Grams per mole for the entire molecule of iron 3 oxide. This is actually iron 3 oxide, right? Now, last one. We'll have here iron, we have carbon, and we have oxygen. How many of each? Well, for iron, we have 2. For carbon, we have 3. And for oxygen, we have 3 times 3. So this would be 9, right? This guy is 16, this guy is 12, and this guy is 56, right? From the periodic table, remember, these are from the periodic table. So how much do we got? So we have in here 112. In here we have 36. And 9 times 16, 144. So 144 and 36. Now we add these numbers and we will get 292 grams per mole. Right? This is the molar mass for iron 3 carbonate, right? CO3 is carbonate, it's a polyatomic ion. All right, let's continue. Now for mass conversions. In mass conversions, it's important that we have in mind both the molar mass that we have just previously seen how to get it, and also the Avogadro's number, right? Remember, Avogadro is also a constant. It's a constant number. And we'll be using 6.02 times 10 to the 23rd. These two things are the pillars, or the, let's call them the pillars of everything that happens for mass conversions, specifically in stoichiometry, right? Why? Because they are the ones that we'll be using in our math, right? So in mass conversions, we're going to be switching the identity of different quantities, specifically from grams to moles or from moles back to grams. But also we will talk about differences between moles and molecules, which is not the same thing, and molecules back to moles. Now, when we talk about molecules, we may also mention this as atoms. The station or the area would be exactly the same if we're referring to molecules or atoms. That would be the same area, right? But it's not going to be the same if we say moles versus molecules, right? Those are two different entities, two different personalities. But still, the question is, how are we going to switch them, right? How are we going to convert from moles to grams, or like, what's the key, or what's the point, or how is actually that we're going to achieve this? We're going to be using these two pillars that we actually just learned how to do. For between grams and moles, we're going to be using molar mass, and between moles and molecules, we're going to be using the Avogadro's number, right? This will be our conversion factor in these cases. Now, let's see. If we're talking about these two guys, we said about molar mass, right? But it's not going to be the same if we're transferring or transforming from grams to moles, which in this case, we will be dividing whatever number we have in grams, we will be dividing it by the molar mass, right? MM is, in this case, is molar mass, right? The molar mass of what? Of whatever it is that you have in the problem, right? In the question. So like in previous examples, like if you had sodium hydroxide, so then you will divide by the molar mass of sodium hydroxide, right? Whatever you get from that division, from that problem, that number will be your moles, right? Now, what happens if you're going backwards, right? Or the other way, if you're going from moles to grams, then whatever number you have in the problem, let's say 2 moles of something, right? Then that number, this 2, you will multiply it by the molar mass of whatever element or whatever molecule you have in there. Let's use the same example of sodium hydroxide. So the molar mass of sodium hydroxide, you will use it to multiply it and get the grams, right? If you're going from on the other side, talking about between moles and atoms, then the number that you're going to be using is the Avogadro's number. So whatever number you have for moles, 2 moles of something, this 2, you're going to multiply it by 6.02 times 10 to the 23rd. And if you're going on the other way around, like atoms to moles, then you're going to divide whatever number you have here, molecules or atoms, by the Avogadro's number. Now, it's important to mention in here that the units for each of these, of grams is grams, of course, moles is mole, and molecules in atom, we will be having actually times 10 to the 23rd, or to any exponent, right? 23, 25, 21. So that number, you're going to actually be using it to make the division, right? You have to actually put in the calculator too. So as you can see, it's important to notice how moles is actually the bridge between these two extremes, right? Between one side, we have grams, and the other side, we have molecules. As you can see from before, there is actually not a direct path or a direct conversion between molecules and grams. We have to actually make first a stop into moles and then convert to molecules, or the other way around, right? We cannot just ignore moles. Moles will always be the center point where all the information needs to first land in there before going to somewhere else, right? So let's do these examples in here. So it says calculate the amount of moles in 84 grams of copper. So copper, what is copper? Copper is an element, and you can find it in the periodic table. So the first thing that we need to know is if we're going to be using molar mass or the Avogadro's number. Since these two guys are actually, like, we can draw like our map, our tiny fraction of a map. This is a mole and atom. Let's use atom, right? So this means that we're going to be using this side of our map, right? So we're going to be using the molar mass on this side. So the first thing that we need to get out is the molar mass of copper. Now you can check the periodic table and you'll get this number. So we can actually use 64, right? For these problems and these examples, I'm using the exact number, so it's easier to relate the number from the periodic table. But in your exercises, you need to actually use the number that is rounded up, right? So what are we gonna do? So if we're going from grams to moles, we're going to actually divide by the molar mass. The molar mass of copper is 63 point, in this case, 63.54. So we're gonna put it in here. And in this case, they're giving us 84, right? So in this case, we're actually gonna have the 84 grams divided by the 63.54 grams per mole, right? So at the end, our answer is going to be 1.32 moles of copper, right? If we actually see in this fraction, I mean, I'm not doing the entire thing, but at the end, you're actually going to be able to cancel grams, and the unit that you will be having as a reminder is going to be moles, right? So at this point, we need to question ourselves, are we done, right? Is this what they're asking in the question? So it says, calculate the amount of moles. So yeah, they're asking for the moles. I got moles, so we're done, right? So this will be your final answer. In this next example, it's actually asking for the opposite. You're going the other way. So it says calculate the number of grams in 8 moles of nickel. So again, from our map, we would have grams and mole. Over here, we have atoms, but we're not going to be using this side of the map. We're just talking about this. And from moles to grams, we actually have to multiply by the molar mass, right? So first step, we need molar mass. Which molar mass? Of nickel in this case. So we can search the periodic table and we will find out that the molar mass of nickel in this case is 58.69. Again, normally for your practice exams and exercises, you will use the rounded number of 59. In here, I just put the number from the periodic table. So we put this in our formula, which would be the 8 moles of nickel times the molar mass of nickel. So we will get pretty much under half a kilo of a nickel in this point, right? That is the equivalent of 8 moles. What about in this case? We're being asked for the atoms in 5 moles of calcium. So let's think about this for a second. So our map said it was gram, then mole, then atom, right? So if we're using only this side of the map, then we really couldn't care less about the molar mass, right? We're actually more worried about what's the conversion factor between these two guys. So which one is it? The Avogadro's number, right? This is the one that's going to be helping us to transform this side of the map. So if we have 5 moles of calcium, and we know that each mole is 6.02 times 10 to the 23rd, then we're going to be using the same number of Avogadros to multiply by each mole, right? Now, if you do this manually, or if you just put in your calculator these two numbers, right, this number and this other, and you disregard this in your calculator, the answer you will get is this guy, right? Because 6 times 5 is 30, right? It's important to know that what you're doing here, and if you just put this times 10 to the 23rd immediately here, this would be incorrect, or at least incomplete, the answer, or not final answer, right? Because remember that the scientific notation rules tell you that the number that should be here on this space should have only one digit, right? Like a maximum of 9, right? You cannot have 10. So what is actually going to be happening, pay attention in here to the 30.1, we actually need to move the dot to the left, right? So this extra movement to the left means that we're going to be adding one additional space in here. So just to let you know, if you do this manually, you also need to change the exponent at this point, right? Now, of course, you can use a calculator and this gives the answer automatically. Just pay attention to what exponent are we talking about, right? At the end, you just put the unit, which is atoms of calcium, according to the question. What about here? We have molecules in 8 moles of sodium hydroxide. It's actually pretty same thing, right? Because we're using atoms and molecules interchangeably at this point. So we're still going to be using the Avogadro's number, and we're going to multiply whatever amount of moles we have in there, in this case 8, by Avogadro's number. Remember, this amount equals to 1 mole, right? So if we're being told that we have 8, so instead of 1, we have 8. So is this same unit times 8, right? That's the logic behind this. Again, pay attention here how the answer changed, or the exponent from this 10 changed from 23 to 24 because this multiplication, right? 6 times 8 is 48. So instead of putting 48.20, you will put here 40 or whatever. So you would put the 4.8 and then the rest you just, round it up to the second decimal. And you move one space from the conversion factor, from the exponent. So yeah, keep in mind that exponent and that you're not missing it from your calculator or from your calculations. Now, what about here? It's already giving you a specific amount of atoms and they're asking you to change it to moles. So we know we're going to be using Avogadro's number, but how exactly? So in this case, because we're already be given a number, we're actually going to be dividing. If you remember the map, we had moles in the center, and in order to get from atom to mole, we actually need to divide this guy, right? So we're going to be dividing by Avogadro's number, 23, right? So this entire thing, well, up to here, right? This entire thing you're going to be putting in the calculator and then divided by this entire thing, right? At the end, the answer should be given something like this, right? With some decimals. Normally, you can have more than 1, you can have 2, that's fine. But it's important that you put the number not with scientific notation. Some calculators will give you the answer also with scientific notation. So if this is the case, you can just change the mode in order for you to be having numbers with decimals, so you can actually use this to put your answer in there. What about here? It's the same, right? So we have the molecules and you're going to moles. So we're still using Avogadro's number and we're dividing the whole thing, right? What about from here? We're actually given the grams and we're asked for the atoms. If you remember the map, we have gram, mole, and then atom or molecule, right? So what they're asking us to do is to get the number of atoms starting from grams. Remember, there's no direct way that we can reach the atom all the way from grams. We first need to make a stop in mole town, right? So we're going to be going from gram to mole. We're going to be dividing by the molar mass, right? And from mole town to the atom, we're going to be multiplying times the Avogadro's number, right? So where do we start? Well, first define what do I need? Well, to answer this, we will be needing the one from the left, which is molar mass, and the one from the right, which is the Avogadro's number, right? So let's find out also the molar mass. So the molar mass of magnesium, we can check the periodic table and we will get it 24.30. For this, you can use just 24. and the Avogadro's number, which is always the same number. Now, let's start. So if we have the grams in here, then remember the first thing that we need to do is divide by the molar mass in order to get the moles, right? Once we have the mole, careful here, it's important to think for ourselves. Are we done? Was this the question? Well, no, the question was for atoms, not moles. So we're halfway there, right? The only thing that we did was get from here, from mole, from grams, all the way to moles. But now we need to go from moles all the way to atoms. We need a second flight, right? We need the connection. So we're going to take this number of moles and then multiply by the Avogadro's number to get the final amount that we're actually being asked, right? So at the end, we get this molecules of magnesium. Well, here, let me change from molecules, let's change to atoms because that's in the question. So at the end, they're asking us for atoms. Do we have atoms? Yes. So this would be your final answer. What about this example? In here, they're giving you the same. So they're giving you grams. You need to go to mole town and then get to molecule, right? Remember, there is no direct connection. But additionally here, they're giving you not the formula, they're giving you the name. So what is hydrobromic acid? Well, hydro, that means is a binary, and then it's acid, so a binary acid. So how do we write that? It's important to know because for this problem, we will be also using the molar mass and Avogadro's number, right? So what's the molar mass of hydrobromic acid? First, we need to get the formula from the name. So if you remember from nomenclature, you will find out that it's an H and a Br, just like that, right? Charges meet, so that's fine. Now we get the molar mass for hydrogen, which is 1, and the molar mass for bromine, which is 80. Together, hydrobromic acid, it's 81 grams per mole. So we get the Avogadro number because we're also going to need it, and we start now our journey. If we begin in grams, that means we're beginning our journey over here, right? So from grams to moles, we divide by the molar mass, which is this number that we have here, right? And this number here is the one in our problem. Once we have the moles in here, we're halfway there, right? So you're here, right? But the destination is over here. So now we need the second flight to get into the atoms. So if we're going over, this is times 0.2 times 10 to the 23rd. That's the Avogadro's number. So at the end, we get this number. Sorry, this is capital. We get this number, and this is it what they're asking us? The molecule? Well, yeah, actually they are, right? So this would be our final answer. What about here? So we have, we're given the atoms and we need to get into grams. So we're going ahead also from side to side of the bridge. So we need first to stop in moles. So we're going to be using both. We need molar mass of gold and we need the Avogadro's number. In here for gold, you can use 197, right? So we'll start our journey now on the opposite side of the bridge. So let's start on molecules. So these molecules is the one that they're being giving us, right? So in order to get to moles, we need to divide, right? Going under, so we divide by the Avogadro's number. And then we need to go over the top all the way to grams. Over is multiply, right? So at the end, we will be having this answer, 242.27 grams of gold, right? That will be your final answer. Always compare. Again, when you're doing this kind of problems, first you need to get them all. So always think, am I done? Well, no, we need the grams. So you need one more step. Final example in here, you're also starting from molecules and you need to get all over the other side. So you need to stop at mole town, right? But pay attention here. What about the molar mass? We need the molar mass, and this is sincerely quite annoying because we have many stuff going on, right? So we have our large formula of situation here. So we have iron times 3, right? We have acetine times 2 because this 2 affects this guy. And also here we have oxygen already having a 3, which means this 3 is going to multiply by this 2. So we're actually going to be having oxygen times 6, right? We get the amounts, we add up. Now that we have the molar mass of our compound, we get our journey. We start our journey, right? So remember, we start in molecules. So we go under the bridge to reach mole town. So we divide, and then once we have the moles, we go all the way over here. So we multiply and get the final answer, which is grams of this compound, right? All right, so hopefully this was helpful to review or to see this for the first time if you're having the course remotely and you missed the class. Or yeah, just to study or to refreshen up these concepts. And yep, so yeah, that's it. Let me know if you have any questions to my mail or during our class, you can also ask about this stuff. All right, thanks.